Yes, Vipul, you are asking, did I teach vector spaces? Yeah, I started talking about vector spaces in yesterday's class. So today I'll continue doing that, right? I'll continue that. Okay, so we are on YouTube. I'm going to start the recording on my computer also. Okay, great. All right. So again, welcome to our your second class. For me, it is the which class is it? I think it's 25th or 26th class. I've stopped. It has started to become difficult to keep track. Oh, I have to share the YouTube link. Okay, somebody with people who can't attend on Zoom for whatever reason. So, okay. So yesterday's was 25. Oh, today is 26. My mistake. Okay, so Vipul, what is your question? Let me see again. Yeah, no, I'm going to talk about that right now. Okay, I'm going to talk about what a vector space is properly. Yesterday, I was just sort of giving an overview. So, online class number 26, October 8th, 2020. Okay, so in yesterday's class, let's just briefly remind you that I went over the rapid history of quantum mechanics, starting from the initial observational observational observations which could not be explained by classical mechanics, then the initial theoretical developments, Planck, Einstein, Bohr, and Sommerfeld. Yeah. So now you can turn your cameras off. Thank you so much for keeping them turned on in the beginning. Then the birth of quantum mechanics with de Broglie, Schrodinger, Heisenberg, and Dirac. And then, of course, much more, a century of work has come. So then I start talking about the mathematical foundations of quantum mechanics. And again, as in yesterday's class, please remember that feel free to interrupt me at any point by just unmuting yourself and asking a question. And if you're watching on YouTube, please feel free to ask in the YouTube chat from time to time. I will be checking that also. Okay, so the core concept of quantum mechanics, the core statement is that systems can be described by, the state of a system can be described by a vector. And once we accept this proposition, then almost everything else about quantum mechanics follows as a result. So once we say a state is described by a vector, we realize that, well, the things that operate on vectors are, well, operators. And what are operators? They are matrices. And so there are different kinds of matrices: Hermitian, unitary, anti-unitary. Now vectors can be either complex or real. And for Hermitian matrices, so for complex matrices, we have this extra possibility of complex conjugation. And that means that there is an extra operation. So in addition to the matrix transpose, we can also have a conjugation. And so this is a transpose, and this is a transpose combined with a conjugation. And there is a special name given for it, which is called taking the Hermitian adjoint or the Hermitian conjugate. And then, so matrices are d-dimensional vectors, and vectors are d-dimensional objects, matrices are d by d-dimensional objects, but in general, the dimensionality of a matrix can be arbitrary, pq, where p and q are positive integers. So for complex numbers, then I explained that, well, we have all the same expressions as we do for real vector spaces, right? And then, so for example, if you take a vector and you take the transpose of the vector, so transpose vectors are described as rows and vectors are described as columns. So if you take these two objects and multiply them, what you get is a number because of the rules of matrix multiplication, right? So because of the rules of matrix multiplication, if you take any vector and it's transpose of any vector and multiply it with any other vector, and of course these vectors don't need to be the same, they can be different, you will always get a single number, which is a scalar. Now, in the case of complex vectors, you can take the adjoint of a vector and multiply it by itself. Or again, these can be two different vectors, but when you take both of these vectors to be the same, in that case, what will happen is the result will turn out to be a sum of real numbers, right? The amplitude of each vector. And so this is an important aspect. This is called the inner product or the scalar product. And for real vectors, the inner product is just V transpose times V, because there is no need to take complex conjugation doesn't do anything. For complex vectors, you have to take the Hermitian adjoint. So then we came to the million-dollar question, which is what is the meaning of vectors, right? And I explained that, well, so that is what we'll talk about today. And I'll also talk about this Dirac notation. What is the meaning of bras and kets, which I explained briefly yesterday. Okay, so let me start with what is a vector space. So what is a vector space? A vector space is a set, okay? It's a set V, right? And with elements small v, which is closed under linear sums, under linear combinations of its elements. Okay, what does this mean? What is a linear combination? It means we can write it like this. So this is the symbol. This means for all u and v in the vector space V. And now, as I said, that we can choose whether vectors are going to be complex or real. So if the vectors are, so when we say for all u and v, a linear combination means that you take the vector u and multiply it by some coefficient alpha, and then you add it to vector v multiplied by some coefficient beta. And this combination, this sum, will also be an element of v for all alpha beta. Okay, and now the question is what are these alpha beta? So alpha beta are elements of either R or C. So if you're talking about complex vector spaces, then these coefficients will be can be complex, otherwise they have to be real. So of course, so the real vector spaces are a subset of complex vector spaces, right? So this is the definition. So it is closed. The set is closed under this operation. Closed means that you take any two elements of the set and you apply the operation to those two elements, and you get another element of the same set, right? So this is the basic definition of a vector space. Now, a vector space. So then we say what is the there is the concept of linear independence. Okay, and so this by the way is known as a linear combination. Yeah, Vipul, you're right. That's exactly what it is. It's a superposition. That is exactly right. Superposition comes from this only. So we have the concept of linear independence of vectors. Which means that, so before talking about this, actually, let me mention what is the meaning of linearity. What does it mean when we say something is linear? There is a linear function on some space. So let's say that you have some set X and another set Y. Okay, and then you have some function from the set X to the set Y. Right. So in this case, for example, our first set is a vector space. Our second set is the set of complex numbers or real numbers. So then the meaning of linearity is that if I have somebody raised their hand, but then they lowered it. So if you have a question, you please ask by unmuting yourself. Okay. So if you have a function, so which is some function of some number of copies of X, d copies of X. So x1, x2 to xd, then the statement of linearity is that this is equal to the sum of those functions operating on the individual elements. And moreover, if you have some coefficients alpha 1, alpha 2, alpha d xd, then this is equal to alpha 1 f of x1 plus alpha d f of x2. So this is a statement of linearity, and the moment I have this kind of behavior, then it follows that I can take any other function which is also a linear function. So this is a linear function. So I can take any other linear function, let's say g, right? Then g and f can also be combined with each other. So g is also a linear function from x, d to y. Then we can take f and g, and we can take linear combinations of a of f and g, where again a and b are some other coefficients, and this will again be a linear function. So this is the nice property about linearity, is that the set of functions on a linear space is also has this property. Okay. Now, what would be the meaning of non-linear? What would be non-linear? Non-linear would be well, if this property was not satisfied. So for example, if let's say fx1, x2 was equal to something like this. So in that case, what would happen is that if you took alpha 1 x1, alpha 2 x2, then assuming that f of alpha x is equal to alpha f of x. Assuming this expression would become alpha 1 times alpha 2 times f of x1 times f of x2, right? So this is a function which is not linear in its arguments. So okay, so anything, for example, if you have some function, let's say f of xy is equal to x square plus y square plus 2xy. This is not a linear function, right? Anything which has polynomials powers higher than order 1, that is a non-linear function. Okay. So then we have the concept of linear independence of vectors. Okay. So what is the meaning of linear independence? Well, linear independence means that let us say that I have a vector v in my vector space, and because of this property, because of this closure property, I can find some other set of vectors, right? So there will be this symbol means there exists, or there is some other set of vectors, let's say ei. Okay, so I is the vector index. It is not the, I'll use something else, I'll use capital I. It is not the component index. So E1 is a separate vector, E2 is a separate vector, and so on. So there is a set of vectors which are also elements of V, such that V can be written as a linear sum of these elements. So we have some coefficients alpha I. Okay, and now here I'm not writing the sum, because we will take it to be implied in many such expressions. When it is not implied, I will explicitly say that it is not. So right, so whenever you have this repeated index, two i's over here, there is a sum over here that is in hiding, but we will not write that down. Okay. Okay, so second. Okay. So 1 second, let me just reorder the pages again. Okay. Okay. Oh, okay, again. Right. So then let me repeat this over here. So for any vector v, there can be a set of vectors, right? And now the thing is that this set of vectors, I have not said how many there are, right? So instead of writing D over here, I should say N, where N is some arbitrary number. Okay, but now remember that if in this expression, the same vector E appears more than once, right? So let's say that I have alpha in this expression, I have two terms. Let's say for alpha I, then EI, and then I have for some other value of the index J, EJ, where E of I and E of J are the same, right? Then any such expression is also proportional to E of I, right? Right, where the coefficients are different now. So these two coefficients would simply add, again by the linear property. So if in this expression, if n is greater than D, and what is D? Where D is called the dimension of the vector space. Right? So what is E of I? E of I is some vector. So I goes from 1 to n, where n is some integer. We don't know what n is. And so let's say that n is greater than D. Okay, where D is a fixed integer, D is the dimension of the vector space. Then what you can do is that in this sequence, you can always take all such combinations wherever the same vector repeats and replace it by a single copy of that vector, right? So what you can do is you can take this sum from I is equal to 1 to n, right? And you can replace it by a different sum where now I is equal to 1 to some other number. To D, where now this alpha prime is, is just the sum of the coefficient for all the repeated vectors. Okay. So now in this expression, we will say, okay, and also this, we'll call that n prime. Okay. So we keep repeating this process until we have reduced this number so that it is as small as possible. Okay. Now, when it is as small as possible, right? So the minimum value of this number, that minimum value is called the dimension. This is not a very accurate definition of dimension. I'll try to make it more. I think mathematically this is the mathematicians would and they would slap me for giving such inaccurate definition. So now conversely, you can also have a situation where there is some minimum number of vectors which are required in this sum, right? So you could have some, so the minimum number of vectors that is required, that is the dimension of the vector space. Okay. And so the statement is that there exists a set of vectors E of I such that for all vectors in the vector space, for any vector V, you can write V as a linear sum of these vectors. Okay. So, and so the assumption here in this statement is that you cannot reduce D by this procedure to any smaller number. Okay. So when you have reached the simplest subset, that is, so you will get the dimensionality. Now you have to keep in mind that, see, these are all mathematical definitions, but they were not given by God. I mean, I don't want to bring God into the picture.
Excuse me, sir.
Yes, who has a question? Who is
Sir,
it?
me, Shantanu.
Uh,
So, sir, you are saying like we can reduce the number, and like what reducing actually is, like I can't grasp it. Like,
no, basically that in this expression, if there are some vectors which are not linearly independent,
mhm.
if they are not linearly independent, then you can express those vectors in some other vector which has fewer terms. No?
Like, but we are saying that linearly dependency means that we can express if they are not linearly independent. How can we express them as the sum of other vectors?
No. They are still linearly dependent, right? They are still linearly dependent, right? I mean, okay, I'll give you an example. Let's say you have. Is my connection breaking up?
No, no, sir, it's fine.
Okay. So let's say you have. Let's take a simple case of a two-dimensional vector space, and let's say you have u is equal to 1 and v is equal to 0, 1. Okay. Now, instead of u and v, let me call this E1 and let me call this E2. Now, in terms of these two vectors, right, you can write down any other element of the vector space, right? Why? Because any element of the vector space is what? It is given by some numbers alpha beta, where alpha beta belong to C. We will work with complex numbers, complex vector spaces, because, well, we are doing quantum mechanics. Then, so then for all such V, or for any V, we can write down, let's say we can write down this expression that A1 E1 plus A2 E2, right? Where A1 and A2 are some arbitrary complex number. Well, not arbitrary, they are some complex numbers. Right. So they are linearly independent if you cannot write them as a linear combination of other vectors. So in this example, again, copy, right? So now you can imagine you don't have to write it in this way, right? So I can take V, let's say V, I can take an explicit example, V is equal to 1, 1, right?
Hmm.
Well, in this case, well, I can write it as E1 plus E2, okay? But I can also write it as in terms of some other vectors, let's say E prime 1, E prime 2 plus E prime 3, where E prime 1 is the same as E1, okay? It was what, 1, 0, I think, yeah. But E prime 2 is equal to 0, 1 half, and E prime 3 is equal to 0, 1 half. Okay. Now, and in this expression, the primes are looking just like numbers. So, So now the thing is that see, V is being written in terms of a sum of, and I'll make these coefficients also different. I'll make this 0.3 and I'll make this 0.7. So now you can see that E prime 2 and E prime 3 are different vectors, right? But the sum of these three vectors can be reduced to this set, right? How? By recognizing that if I take E2 and E3 and add them together, what will I get? If I take E prime 2 and E prime 3 and add them together, what do I get? I get E2. So these two vectors are not linearly independent, right? Because they are both multiples of E2. This is 0.3 times E2 and this is 0.7 times E2. Is it clear?
Yeah, sir. No,
okay.
it's.
So now I can't reduce the number of terms in this expression to anything less than 2, right? Okay. Now, okay. So this is the thing. Then we have the concept of, so such a set of vectors, such a set of linearly independent vectors is called a basis of V. Okay. Does the dimension of a vector V? No, it doesn't mean that. So no, not at all. The dimension of a vector V is the number of rows, whether they are zero or non-zero. So this vector E1 is a two-dimensional vector. Okay. And if I have some vector V, which is 1, 0, 0, 0, whatever, the dimension of this vector lives in a vector space which has the number of rows. Okay. So now we have a basis of V, right? But you can have more than one basis. You don't need to have, this is not the only basis, right? This set of vectors is not the only basis. I can have a different set of vectors. Let me say E prime 1 is a different, is a vector which is, let's say, 1/2 comma 1/2, and E prime 2 is 1/2 comma minus 1/2. Okay. This is also a set. These two vectors are also linearly independent. But you can write the previous set, right? In the previous case, what was E1? E1 was 1, 0, right? So this can be written as a linear sum of these two vectors, E1 plus E1 prime plus E2 prime. And the other vector, E2, which is 0, 1, can be written as E prime, so E1 prime minus, well, E prime 2. Okay. right? So these are two different sets of basis vectors. This is one set of basis vectors, and this is a different set of basis vectors, right? But the number of these basis vectors is the same. That doesn't change. The dimensionality of the vector space is not going to change. Okay. So you can have, and of course, all of these things you should know by heart. This is all very elementary stuff. So, and how are these two related? They're related by a linear transformation, right? So what is a linear transformation? Can we say that the number of variables which we are using to write a vector is the dimension of the vector? Yeah, sure. The number of degrees of freedom. So the number of degrees of freedom. So for example, here is the number of rows. That's the dimensionality. Okay. Aman, I'm going to mute you unless you have a question. If you have a question, you can please unmute yourself. Okay. And ask. Okay. So then we have the concept of linear transformations. Linear transformations are matrices which act on these vectors. And now, but before that, let me talk about orthogonality. So what is orthogonality? Orthogonality means, remember I told you there is a concept of an inner product. Vikram, you don't need to raise your hand. You can just ask the question, unmute yourself and ask the question. Vikram, you have a question or not? I don't know what that question means. We can write infinite solutions. I don't know what that means. There is nothing infinite right now. Okay. Again, this is meant to be a review of concepts. All of these concepts you are supposed to have learned them in high school and then in BSc. So what is orthogonality? Orthogonality is a statement that if I take any two vectors, u and v, and I take the inner product, which you normally call the dot product, if this is 0, then we say that the vectors are orthogonal. Are orthogonal to each other, right? So in the previous example, you can see that these two vectors and these two vectors, they are both orthogonal to each other, right? If you take the dot product, there is 0. So, and then we have the concept of the norm of a vector. The norm of a vector is the square root of the inner product of the vector with itself. And now the thing is that the way I have written this kind of a definition, when I write u dot v and u dot u, these definitions, they apply only to real vector spaces. Okay, why is that? Because let's say if u is a complex vector, so it's an element of CD, CD being d copies of complex numbers. So that is a d-dimensional complex vector space. So if u is an element of CD and I take this u dot u, what is the meaning of u dot u? It is actually u transpose multiplied by u. And what will that give me? That will give me u1, u2, ud. This is the transpose times the vector. What does this give me? u1 square, so on, plus ud square. So now the thing is that if this is these are complex numbers, then this in general will also be a complex number. So if this is a complex number, but then if you take the square root of this, that will also be a complex number. Okay. So now, but we require, for many different reasons, that the length of the vector must be real. So if we require that the length of the vector should be real, so Vipul, because u1 and u, all of the coefficients are complex numbers. If I take some complex number and multiply it by itself, we can get more complex numbers. One second, Chinmay. So if you take u1 and ud, right? I mean, if you have a set of complex numbers, if you take a complex number you multiply by itself, z square, what is this? This is a complex number, right? If I take two complex numbers and I multiply them by themselves and add this, then this is also a complex number. This will not be a real number, no? Okay. Chinmay is asking, can we say that v and u are linearly independent if a plus bu is equal to 0, then a and b? Yes, sure. That is the definition of linear independence. That if you have a times u plus b times v, and and we say that this is equal to 0. So if this implies that either a or b is equal to 0, then in that case, u and b are linearly independent. Something in the WhatsApp. Okay. So now, okay, so we require the norm of the length of the vector to be a real number. So because of that, we need to define this inner product differently. We can't write it as, we cannot write the inner product no, the square of a complex number is not a real number. Please, guys, you need to go back and revise your basic math. This is all very, very elementary things. So the inner product of two vectors which are complex cannot be defined in terms of u transpose u. Instead, it has to be defined as u complex conjugate transpose times u, because then this will be equal to u1 complex conjugate u1 plus ud complex conjugate ud. So somebody asked that, is the square of a complex number not complex? Okay, so let me answer that. This is how we write complex numbers, right? So if I take the square of this, what do I get? I get a plus ib times a plus ib, which is equal to a square minus b square plus 2 times iab, right? So this is not going to be a real number, right? If this is a real number only if either a or b or both are 0. Okay. But if I take the complex conjugate, what is the complex conjugate? It's a minus ib. In that case, what is this? This will become a square plus b square, which is a real number. Okay. It's okay. I mean, you can ask me these questions no matter how simple or elementary they are. I'll just have to cover them. Okay. Because, well, I want all of you to be on the same page. Okay, so the inner product is then defined in terms of taking the complex conjugate transpose, the Hermitian adjoint of the vector, and multiplying by itself. And so this guy will always be a real number. Okay. Okay, so it is 9 a.m. Let me ask you guys, do you have any class right now? Anybody? Yes, no? Is there anybody who has a class right now? Okay, so I'm going to continue. Okay, we have a lot of material to cover. We have a class at 10:30, so we have a lot of material to cover. Okay, so I'm going to continue right now. Okay, so what we are going to do now is we're going to work with what is known as this bracket notation, also known as Dirac notation. Okay, so what is the meaning of this bracket notation? If we have a vector u, we write it like this, some set of coefficients u1 to ud. Okay, then this is written in a slightly different notation, in this bracket notation, as, and this is called a ket vector. Okay, then if you have a transpose, if you have a column vector, let's say some vector v, so if you have a column vector v1 vd, this is called a bra vector. Okay, now what is the point of using this notation? What it means is that, well, so if you have a bra vector u and you have a ket vector v, then I can write down this combination, which is called the inner product. And the inner product, sorry about that. This inner product is what? Well, it's the usual expression that we had earlier, u1 v1, right? It's what you call the dot product, ud vd. This is the definition of this quantity. Okay. Yeah, you can leave if your network is bad. If you can't watch for whatever reason, you're free to leave. If you can watch on YouTube, that would be fine. Otherwise, I will share the notes with you later. You can go over them. And of course, we have a lot of, well, what to do in this day and age. We have to do, we all have this compulsion, right? Okay. So Vipul is, bra vector is V. No, it's not V. Here the B is a ket vector. I've already told you that you can't just change things as you like. This is the definition of bracket. Okay. If you don't like it, you can know what to do. So this this is called a bracket. Okay, it comes from the word brackets, right? These are brackets. These are all examples of brackets. Okay, so this is the inner product. Now, so one can ask that if you have a certain vector u, then what does the bra of u look like? Okay, so now this is the thing, that if this vector has components u1 to d, then the bra vector has components u1 complex conjugate to ud complex conjugate. Okay, so what is this? This is equal to the vector u transpose complex conjugate. This is very important. Okay, so this is the definition. Okay, this is the definition of what it means to have a bra vector. All right, this definition means that if you take the inner product of the vector with itself, okay, so this is the inner product. This is how I define the inner product. What is this inner product? This inner product becomes which is an element of real numbers. Yeah, so this is the norm. This is the norm squared. So this is called the norm of u squared. Okay, so this is called so this is the norm, the length of the vector. Okay, so u is the Dagger matrix of, yeah, exactly. So you would write it like this: u is equal to u dagger. Okay, but this also means that the reverse is true. The reverse is also true, right? So if I take the complex conjugate transpose twice, I will get the same object. Okay. All right. So this is the definition of these guys. Now we come to the question of matrices and so before that, so in this notation, if we want to say that two vectors are orthogonal, we would write that as in this way. This is orthogonal. Okay, and then we also have the concept of normalized vectors. So what is a normalized vector? Normalized vector has norm 1. Okay. These are the unit vectors. Right? So now remember that we talked about having a set of basis vectors. So I can write U as a linear sum of basis vectors. So I have some set of basis vectors. Now I will write everything using this bracket notation. Okay. So I have a set of D basis vectors. Okay. And I will write it like this: E of I, where I goes from 1 to D. And again, so I'll put the index on top like before. So I labels the vector. It doesn't label the components of the vector. Please keep that in mind. Very important to remember. So then if you have any vector in this vector space, that vector can be written as a linear sum of these EIs, where alpha I are complex coefficients, right? Then you can ask, well, what is this? What is this guy? Well, this guy is alpha IEI Hermitian adjoint complex conjugate transpose. What is this? Well, the Hermitian adjoint is also a linear operation. So if I take any two vectors u and v and I take their sum, and then I ask what is the transpose complex conjugate of their sum, well, that is equal to so this is a linear operation, right? So it distributes over the elements. And what is this? This is equal to, okay. So what does this expression become? This expression becomes, what will happen to the alpha I? They will also become conjugated. And they are just numbers. So just, I don't put a dagger, I put a star. Times E of I. Right? So this is just saying that, well, the complex conjugate, if you have something which is a sum of some other things, and you take the complex conjugate of that thing, it is the sum of the complex conjugates of the whatever those things are in the first sum. Okay, let me add some pages. Okay, so what are the properties of this complex conjugation? We have that this is the first relationship. Then what else? If I take any complex number multiplied by this, I can write it like this, right? Where this is alpha times the components of the vector u. So as I explained here, if you take this guy, this is, so you can, if you are ever in doubt, you can work out all of these expressions manually, explicitly, by writing them out in terms of components. Okay, so if I write it out in terms of components, what do I get? Right? So this means that if I take okay, so let me write that on a new line. Sorry about that. I was getting a call on Skype on Google Duo. Why do we use bracket notation instead of just putting a dagger? It would be easy. Well, that's a good point, Chinmay. I don't know why. why we do these things. Okay, I don't know. I don't know. I think that as you continue to see the expressions, you will realize that they look simpler in the bracket notation. That's why people use it. If bracket notation was more complicated than the adjoint notation, people would not have used it so far. No? It's just like a law of evolution, right? If something is more complex or harder than something else, then the people will follow the easier path. So if I ask what is the complex conjugate of this guy, well, that is the row vector whose elements are this. Now, this can be written as, now remember that complex conjugation is also a linear property. So if I have Z1 plus Z2 and I take complex conjugate, what do I get? I get Z1 complex conjugate plus Z2 complex conjugate. So the linearity of complex conjugation. Okay. And so because of this, this expression can now be written as U1 star plus V1 star, U2 star plus V2 star, and then UD star plus VD star, right? But this expression now I can write as a sum of two vectors, U1 star, U2 star, UD star plus the vector V1 star, V2 star, VD star. And what are these two vectors? The first vector is okay. QED, that which was to be shown, right? So we wanted to prove that this expression is true, and that is what I did here, right? I think I'm going to stop here. I don't want to like try to cram too much material into one class. I don't think that would be helpful. Okay, so please ask me any questions. So I think this review will have to take another 2 or 3 more classes. I think the BTech students will be very happy that they don't have to come to class again for some time. Okay, questions? No questions? Okay. Can I swipe? Okay, can I go back a little bit? Okay. Yeah, that is true. There is a lot of content that is covered and you can't see it all. So these are the things I have talked about today. So I started with linearity of functions, linear independence of our vectors. Then what is a vector space? Okay. So tell me where to stop, Shantanu. The last proof. Okay. This one? Mhm. Okay, so is that fine? Do you have any questions about that? The assignments you have to submit on Moodle. So I will go to Moodle and I will make a new assignment so that it has a submission date and everything. And what you have to do is you have to write down the assignment answers on sheets of paper as always. Take scans of that, take photos, and then upload that on the assignment page. So I will share the link for that later. Okay. Okay. Are there any questions? Well, okay. So I'm going to stop the recording and the live streaming.